Plunge into complex ideas, pull out the crucial bits, and, well, give you a shortcut to being genuinely informed. Today, we're not just looking at a math problem. It's more like an unsolved mystery, one with $1 million prize attached. And maybe surprisingly, it actually underpins, the very structure of numbers themselves. Think about this. What are those prime numbers, the ones that seem scattered totally at random? What if they actually follow some kind of secret, predictable rhythm? And what if the key to hearing that rhythm, to understanding it, was hidden inside a seriously complex mathematical function? So our deep dive today is all about a huge moment in 1914, a theorem by the brilliant English mathematician G.H. Hardy, concerns these things called zeros of the Riemann zeta function. And look, this isn't just a story about equations. It's really a tale of human curiosity, I think, intellectual daring, and this ongoing search for a kind of abstract beauty.
Absolutely. And Hardy's work, you see, it's so compelling because of where it sits in history. It was a genuinely glorious moment, a real moment of hope, actually, especially in the context of one of science's biggest, most stubborn problems, the Riemann hypothesis. For decades, this hypothesis just seemed like this massive wall, impossible to climb. It resisted everything thrown at it. And Hardy, well, his theorem gave the first real, undeniable crack in that wall.
Right. So our mission for you listening in is to unpack why Hardy's breakthrough was so important. We want you to really get its connection, this deep, almost mystical link to prime numbers, and to see how it just completely shifted the mathematical landscape, opened up new ways of thinking. And yeah, we promise we'll do it without drowning you in jargon. Think of this as your fast track, your shortcut, to understanding something complex, beautiful, and honestly still really relevant today. Okay, so let's dig in. To really get Hardy's achievement, we kind of need to start at the beginning, right? With the prime numbers themselves, the basics. And then we need to talk about this almost prophetic vision of Bernhard Riemann.
Exactly. The story really starts with primes, the atoms of arithmetic, as they're sometimes called. These are the whole numbers bigger than 1 that you can only divide evenly by themselves in 1. So 2, 3, 5, 7, 11, and so on. They're the basic units. You can't break them down further. Every other whole number is built from them.
Right, exactly why they're called atoms. Like take any whole number, 30 for instance. It's not just 30. It's 2 times 3 times 5, that specific combination. Or maybe 91. Looks prime maybe, but nope, 7 times 13. This idea that primes are the unique building blocks, it's ancient. I mean, Euclid proved there were infinitely many primes over 2,000 years ago. It's fundamental stuff. And here's the kicker. Here's where the real mystery starts. What's always baffled mathematicians is, well, how they're distributed. There's no obvious pattern. They just seem to pop up almost randomly along the number line. Between 1 and 100, you find 25 primes. Okay. Then 100 to 200, there are 21, a bit fewer. But then jump way out, like between 10,000 and 10,100. Only 2 primes there, just 2. Sometimes they clump up. Other times there are these huge gaps. Deserts with no primes. So, I don't know, it's like looking at stars in the night sky. Seems random at first glance, right? But you can't help feeling there might be some hidden order, some, cosmic rule governing where they appear.
And that apparent randomness, or maybe the hidden nature of their pattern, that's what's driven number theorists for centuries. Millennia, really. It's this deep search for order in what looks like chaos, trying to find the invisible structure connecting these primes, the rhythm in the noise. And this whole challenge, this long history, it really set the stage perfectly for Bernhard Riemann.
Okay, so Riemann. And to get to his idea, we need this other piece, the Riemann zeta function. Let's maybe start with something simpler, the harmonic series. 1 plus a half plus a third plus a fourth and so on forever. Lots of people might remember this series, even though the terms get smaller, it actually, it diverges. It just keeps growing slowly towards infinity, never settles down.
Right. Now imagine tweaking that. Instead of just 1 over n, you do 1 over n raised to some power. Let's call it s. So you get 1 over 1 to the s plus 1 over 2 to the s plus 1 over 3 to the s and on and on. That infinite sum is the Riemann zeta function. We write it as thus. And here's the crucial bit. S isn't just a regular number. It's a complex number. It has a real part and an imaginary part, like a point on a 2D map. This complex nature is absolutely key. It gives the function depth, allows patterns you wouldn't see on just a simple number line, and it turns out if the real part of this complex number s is greater than 1, then this infinite sum actually works. It converges, it adds up to a specific finite number.
Okay, so it works for some numbers, but mathematicians, they don't stop there, do they?
No, definitely not. While that series definition is the starting point, the real power comes from something called analytic continuation. It's not exactly magic, though it feels a bit like it. It's a rigorous way to extend the function's definition. Think of it like having a perfect, detailed map of just one small neighborhood. Analytic continuation lets you logically deduce the map of the entire city, making sure everything connects perfectly, even the parts you haven't explicitly seen in the original definition. This is vital because the zeta function's deepest secrets, especially its link to primes, aren't in that little corner where the series works. They're spread across the whole complex plane. So this process lets us define ZA almost everywhere for nearly all complex numbers except for one single point, S1. And that makes it an incredibly powerful tool.
And this is where Riemann comes in, mid-1850s. He takes this powerful extended zeta function and asks this just huge question. For which complex numbers S does this function actually equal 0? Where does its output become 0? And these input values, these S numbers, are what we call the zeros of the zeta function.
Exactly. And 0 here doesn't mean nothingness. It means the input values that makes the function spit out a 0, like where a curve crosses the horizontal axis on a graph. For simple functions, finding zeros might be easy. For the zeta function, it's profoundly difficult. These zeros are like hidden landmarks in this complex landscape, and Riemann immediately found some, what he called the trivial zeros. These are easy to find. They're at the negative even integers, -2, -4, -6, and so on. Interesting, but, well, relatively simple. The real mystery, the ones connected to the primes, are the non-trivial zeros, and Riemann noticed something incredible. Every single non-trivial zero he could calculate, they all seem to fall within a specific vertical strip in the complex plane, the critical strip. This is where the real part of S is between 0 and 1, not less than 0, not more than 1, just in that band.
But he went further than just noticing the strip, didn't he? That's where the hypothesis comes in.
He did. This is where his genius just takes flight. He didn't just observe the strip. He conjectured. He made this incredibly bold guess based on his calculations and deep intuition. He proposed that all these non-trivial zeros don't just lie somewhere in that strip. They lie perfectly on a single line right down the middle of it, the critical line. This is the line where the real part of S is exactly 12, precisely halfway across the strip. Imagine the entire complex plane. His guess was that all the really important zeros, the ones holding the secrets, are lined up perfectly along this one infinite central line, an extraordinary claim of hidden order.
So that's the Riemann hypothesis. And as you said, it's way more than just some abstract puzzle for mathematicians. It connects deeply to the primes.
Oh, profoundly. The connection is intricate. People sometimes say the zeros of the zeta function conduct the music of the primes. If the hypothesis is true, it essentially means the primes are distributed as smoothly, as regularly as possible. The static, or noise, in their distribution is minimal. It would give us the most precise way possible to predict how primes are scattered. It would revolutionize number theory. It could have huge implications for cryptography, maybe even physics. It's such a foundational question about how numbers work that, yeah, there's a $1 million prize from the Clay Mathematics Institute for a proof.
$1 million.
Yeah.
But for decades after Riemann proposed it in 1859, nothing. Well, not nothing, but no proof. Just this kind of frustrating holding pattern.
That's a good way to put it. A lot of brilliant work was done. People gained insights. But proving the hypothesis itself, it seemed impossible. They did manage to calculate more and more zeros using, well, painstaking methods at first. And every single one they found was on the critical line, hundreds, then thousands. But, as mathematicians, we always have to say, checking a few thousand, or even a few billion, isn't proof for infinity. It's strong evidence, suggestive, but not definitive proof. Before Hardy came along, people knew there were infinitely many zeros somewhere in that critical strip. That was proven. But nobody, absolutely nobody, had managed to prove that even 1 zero had to be on the critical line itself, let alone infinitely many. It was like astronomers seeing weird planetary orbits suggesting a hidden planet, but having no mathematical proof it must be there. The hints were strong, but the certainty was missing.
So the mathematical world was just stuck, staring at this critical line thinking, they're probably all there, but unable to prove it. Utterly stuck.
Pretty much, yeah. That was the situation. A huge, tantalizing problem right at the heart of mathematics, and no clear path forward.
And onto the stage walks G.H. Hardy. Godfrey Harold Hardy, a major figure in English mathematics, Cambridge Doan. Apparently quite a character, too. The atheist loved cricket, very particular views, and famous for his love of pure mathematics. He famously said he hoped none of his work would ever be useful, which is ironic given how fundamental it often turned out to be. He just loved the beauty of it.
He was a purist, absolutely, driven by elegance, by the inherent beauty of mathematical truth. And the Riemann hypothesis was right up his alley, deep, beautiful, challenging. There's that great story about him in World War I, right? About to take a dangerous boat trip across the North Sea. So he sends a postcard to a colleague. basically saying, have proved the Riemann hypothesis. His reasoning, as an atheist, was delightfully twisted. He figured God wouldn't let him die covered in false glory for solving math's greatest problem if he hadn't actually solved it. So God would have to ensure he survived the trip just so the record could be set straight. His own little mathematical life insurance policy. Shows his wit, I think.
That really captures him. But, okay, jokes aside, what he did actually prove in 1914 wasn't the full hypothesis, but it was still enormous. A real game changer after 50 years of waiting.
Oh, monumental. It sent shockwaves, in a good way. Hardy proved rigorously mathematically. There are infinitely many zeros of the Riemann zeta function on the critical line, the line where the real part is exactly 12. Now, remember, the hypothesis says all non-trivial zeros are there. Hardy didn't prove all. But proving infinitely many was the first massive step. It showed the critical line wasn't just a guess based on the first few zeros. It was fundamentally important, a real highway for these zeros. It was the first solid mathematical proof that Riemann's intuition was likely correct. Real evidence.
Wow. So not just one oasis in the desert, like we said, but proof of an infinite chain of them stretching out. Hope confirmed, in a way. But, okay, the big question then is, how? How do you prove something infinite like that? You can't just list them all out. How did he do it?
Right, you can't count them one by one to infinity. Hardy's approach was clever, it was indirect. He didn't directly find the zeros. He used a different tool, a related function. It involves something called Hardy's z function and also connections to theta functions, which are other important objects in analysis.
Okay, z function. Can we unpack that a bit? How does that help find zeros on the critical line?
Well, the problem with the zeta function on the critical line that's 12 plus it, where t is the height up the line, is that its value is a complex number. As t changes, this complex value kind of spirals around in the 2D complex plane. It's really hard to tell exactly when that spiral passes through the origin, which corresponds to a zero. Hardy's brilliant idea was to define this related function z, which is real valued. It essentially captures the magnitude and phase information of the zeta function on the line, but squashes it onto the real number line. Think of it like taking that complex spiral and somehow projecting its key behavior onto a simple wave moving along the x-axis. And the crucial property is zt equals 0 if and only if the original zeta function, 12 plus it, equals 0. So the complicated problem of finding complex zeros becomes the simpler looking problem of finding where this real valued wave, zt, crosses the x-axis.
Okay, so instead of tracking a spiral in 2D, you're just looking at a wave on a line and asking how many times does it cross 0?
Precisely.
All right.
And to prove infinitely many zeros on the critical line, Hardy had to prove that the zd function crosses the axis, changes sign from positive to negative or vice versa, infinitely many times as t gets larger and larger.
And how did he prove that? Still seems hard to show it happens infinitely often.
This is where the real genius comes in. He didn't track the crossings individually. He used an even more indirect method involving the moments of the z function. A moment is basically a kind of average value of the function raised to a power over some interval. So the second moment is like the average of z squared, the fourth moment is the average of z to the fourth power, and so on. Hardy managed to prove, using some pretty deep analysis, that certain moments of z, specifically the even ones, like the second and fourth, get very, very large as e increases. They grow without bound. Now think about what that means. If the average value of z squared or z to the fourth is huge, then the function z itself can't be spending most of its time close to 0. If it only crossed 0 occasionally and stayed small otherwise, its average powers would also be small. The fact that these average powers had to be large forced the conclusion that zt must be making large excursions away from 0. It must be oscillating wildly, swinging back and forth across the axis. And if it oscillates wildly enough to make its average powers huge, it must cross 0. Not just once, but again and again, infinitely many times.
Wow. That's elegant. So the sheer magnitude of these average values, these moments, mathematically forces the function to cross 0 infinitely often. It's like you prove a storm exists by measuring the immense total rainfall without needing to count every single drop.
Exactly that kind of reasoning. It's a proof by analyzing the function's overall behavior, its statistical properties, if you like, rather than pinpointing individual zeros. A truly profound piece of analysis, and it worked. It gave the first proof.
Okay, so Hardy proves infinitely many zeros are on the line. Amazing. But does infinity mean, 1 every billion units? Or are they more common? Did his work hint at the density?
That's a crucial follow-up question. And yes, Hardy, working with his close collaborator J.E. Littlewood, did push further on that. They established what's called a lower bound. They showed that the number of zeros on the critical line up to a certain height t grows at least as fast as some constant times t. Now we know the total number of zeros in the whole critical strip up to height t grows roughly like t2 times log t. Comparing Hardy and Littlewood's result with the total suggested that a significant chunk, a non-negligible fraction, of the zeros really were on that line. Not just infinitely many, but a substantial amount. And then, fast forward to the 1940s, the Norwegian mathematician Ethel Selberg achieved something even more remarkable. Selberg proved that a positive proportion of all the non-trivial zeros must lie on the critical line, not just at least t, but a definite percentage, like say at least 1% or some fixed fraction of the total number of zeros are guaranteed to be on that line. That was a massive strengthening. It meant the critical line wasn't just populated, it was densely populated, a major highway indeed.
And moving from the purely theoretical, people actually started finding these zeros with computers, right? Hardy's work must have fueled that.
Oh, absolutely. His proof and the methods he and others developed gave a huge boost to computational efforts. It showed the critical line was the place to look. People like Alan Turing were fascinated. In the 30s and 40s, even before modern electronic computers, Turing was involved in designing mechanical calculators specifically to compute zeros of the zeta function. Shows how important it was seen to be, even then. And since then, the progress has been just, well, exponential. We have incredibly sophisticated algorithms now, like the Riemann-Segal formula, running on supercomputers. And they verified that the number keeps growing, but certainly the first several trillion non-trivial zeros are exactly precisely on the critical line to incredible accuracy.
Several trillion. That number is just mind-boggling. It feels completely convincing. But, as you always remind us, a trillion, even 10 trillion, is not infinity. That crucial mathematical caveat. Absence of evidence isn't evidence of absence. There could still be one off the line way, way out there.
Small laugh? Precisely. That's the discipline of mathematics. The numerical evidence is overwhelming, truly. It would be astonishing if the hypothesis turned out to be false now, but astonishment isn't proof. We still need that one final, rigorous argument that covers all infinitely many non-trivial zeros. That's the million-dollar challenge. But Hardy's legacy, it's immense, not just for this 1914 theorem, huge as it was, but also for his whole philosophy, celebrating mathematical beauty. His collaboration with Ramanujan, another legendary story, brought incredible insights. He really championed mathematics as this quest for elegance and truth. And the 1914 result on the zeros, it stands as one of his peak achievements, perfectly embodying that philosophy.
And for us, thinking about this journey, Hardy's proof really solidified things. It gave mathematicians, and really all of us interested in these deep questions, the confidence that, yes, the critical line is special, it's the place. It turned Riemann's inspired guess from a foothold into a real pathway, even if the end of the path is still out of sight. So here we are today, trillions of zeros checked, powerful theoretical results like Hardy's and Selberg's, yet the Riemann hypothesis itself remains unsolved. That prize is still waiting.
Still waiting. And the reason it continues to matter so much goes beyond pure math. As we touched on, there are connections, some proven, some speculative, to physics, to the statistics of energy levels in heavy atoms, potentially to quantum chaos. Cryptography relies on the difficulty of factoring large numbers, which is related to the distribution of primes, which in turn is governed by the zeros. Understanding the truth of the Riemann hypothesis could fundamentally alter our picture of how numbers behave, how patterns emerge. It's a deep question about the orderliness of the mathematical universe, and Hardy's 1914 theorem remains a cornerstone in that quest, a vital piece of the puzzle, reminding us that even with the biggest mysteries, progress happens. Breakthroughs are possible. Hashtag tag outro outro.
So what a journey. From the ancient puzzle of the primes to Riemann's incredible vision connecting them to the zeros of his zeta function, and finally to G.H. Hardy's landmark 1914 proof, he showed definitively that infinitely many of those crucial zeros do indeed lie on that critical line. It wasn't just a guess, it was mathematically true for an infinite set. A huge step forward, like reaching a solid base camp high up on a mountain that many thought might be unclimbable. And today, those zeros of the Riemann zeta function, they still challenge us, don't they? They're like these points of light in the complex plane holding secrets about numbers. Hardy's achievement really was to light up a path, proving that these points aren't just scattered randomly. Infinitely many lie along that one hidden, beautiful line. A line that continues to guide the search for deeper understanding.
Exactly. The map is still incomplete, the final proof elusive. But the quest, inspired by minds like Riemann and Hardy, definitely continues.
Welcome to the Deep Dive.